Hello, dear students. I am Samir Velankar. I welcome all of you to this video on the topic stack data structure. Now, stack data structure is used for storing data, obviously, because it is data structure. Whenever we see anything is a data structure, then it has got arrangement of data, or basically, it is used for storing data. So, stack is basically used for storing data, but data is stored in last in, first out manner, LIFO manner. What it means is whatever you store last in the stack is always taken out first from the stack. So, last item going in the stack will be the first item to come out. We have got examples of stack all around. For example, the SMS box of our cell phone is a very good example of stack. Whenever a new SMS arrives, then the latest SMS, the last SMS that arrived in our cell phone is always shown at the top, isn't it? Or the mailbox is a very good example of a stack. As the mail comes in, new mail comes in, the new mail is always shown at the top. That means the last mail arriving has become the first mail to watch. So basically, how do you create this stack in our computer program? Is that one of the methods to create the stack is by using array, and another method to create a stack is by using linked list. Now in this video we will be creating stack by using an array. Now you notice the picture drawn on the right hand side. I have an array A here, A of size equal to 5. Let's say size is a constant I have declared, and the value of size is 5. So the array elements are from 0 to 4 as shown in the diagram, and there is one integer variable, simple integer variable called top. All right. So these two things, array of some fixed size and top which is integer, both both of them make a stack. So in case we are asked what is a stack, you should say stack contains array of some fixed size and an integer called top. Integer counter, many people call this top as counter of the stack. So that's what I have shown in the box there up. Now this top counter initially is -1. Okay. Now I'll tell you the significance of top. What is top indicating? Top is a counter. Just imagine we push. That's the word actually. Whenever we put any new item in the stack, we always say we are pushing a value. We never say we are inserting a value in the stack. Although it is insert, but we always use the word push. So push an item in the stack. Let's say we push 10 in the stack. So if we are pushing 10 in the stack, then 10 will be pushed in such a way, this new value 10 will be pushed in such a way that 10 will go in the 0th element. Suppose after ten we push 20, let's say. Then 20 will be pushed in such a way that it will go on top of 10. So 20 will go at first element. Okay. Now imagine these are the values we have pushed. We have pushed 10 and 20. Then the value of top is going to be 1. Now top is 1, indicating that first element of the array where I am pointing to is the topmost element used in the entire array. So anything above this element is not yet used in the stack, isn't it? Now just imagine we push one more element. See, clearly I am using the word push instead of insert. Suppose we push a new element 30. Then 30 will go and sit on top of 20. So 30 is stored at second element. Then the value of top will be no more 1. The value of top will become 2. Check that top is now 2, indicating that the topmost element stored in the array is at position 2. So anything above the position 2 is not yet used. That's the significance of top counter. It tells us which is the last element. Yes, which is the last element pushed in the stack. So last element pushed is the second element, which is 30. Now, initially, you know that as we start our program, there is nothing in the stack. Stack is empty. In that case, any program on stack should start with the initial value of top. Initial value of top should be -1. Now, what do you understand when top is -1? Check how logical it is. Top is -1 means even zeroth element of the array, even this lowest element, zeroth element of the array is not used. So forget about the elements above them, correct or not? Even the zeroth element is not used. That means top is below that element. Top is -1. So whenever top is -1, we say stack is empty. Whenever top is -1, stack is empty. Okay. Now there are two operations possible on this data structure. The operations are push, where we are adding some element in the stack, and pop. The second operation is pop, where we are taking out an element from the stack, deleting an element. So let's see an algorithm to push an element. Very simple, nothing fancy about it. Very easy topic. See that we are pushing some value x. See the bracket. X has been written. Let's say this x is 10. We are pushing 10 in this stack. Then we first check what is the status of the top. Check the if statement. We ask is the value of top equal to size -1? Now in our example, check that size of the array is 5. Yes, size is 5. That's why the elements are 0 to 4 in the array. So we are asking is top equal to 4 because size -1 here is 5 -1, 4. But currently you observe the diagram of the stack, top is -1. So the condition is false. Top is really not equal to 4. So we land in else and we will proceed to push the value 10 in the stack. See how easy is this else portion. There are hardly two statements. Top should become top plus 1. So top which was -1, check I am updating the value of the top. Top which was -1 will increase by 1. So top will become 0. And the next line says a top should become x. A top means A0. A0 should store the value 10. And that's it. That's the end of else and end of the push algorithm. So each time you call push algorithm, what happens is top increases by 1. It's just a counter. Top increases by 1 and that element to which top is right now pointing, that element of the array stores x. As simple as that. So imagine you call push algorithm again and this time you want to insert 20, sorry, push 20. So x is 20. Then what are the two operations? Top plus plus, that is top plus 1. So top which was 0 will now become 1. And a top equal to x, that means a1 will become 20. So simple. Now just keep calling pop for 2 or 3 times. Let's sorry, not pop, I'm so sorry, push. Let's call push 2 or 3 times. Let's push 30. Then what will happen? First top will increase if you are pushing 30. So top will become 2. It was 1, it will become 2. And second element of the array is going to store 30. So what if you push 40 and 50 also? Let's say 40 is pushed and 50 is pushed. Now do you understand? Now do you understand? The value of top by now has reached 4. It is 4 now. Now just imagine you call push. You want to push 60 in this stack, but hello, there is no room in the array. Check that the array is full. We call such situations as stack overflow. When the stack does not have any room to accommodate a new value, we say it is overflown. How will it work now? Let's say we are pushing 60, x is 60. Then check the first if. The if written here is going to check whether top is equal to size -1. Notice the value of top is 4. and size minus 1 is 5 minus 1, which is also 4. So what it means is we have already used fourth location, location number 4 of the stack, and now there is no element above that. So we are going to announce stack is overflown, and we will not go to else and will not increase top and push the value. So that's how easy it is to push an element in the stack. The summary, I always tell the students, the summary of the push operation is hardly 2 lines. The 2 lines are, if you have a stack, if you have a stack, and imagine top is presently over here, top, and you want to push one value, then first of all, you increase top by 1. Top should become top plus 1. And at A of top, at the topmost element, you put some new value. The new value may be 70. So these are the 2 lines which summarizes the push operation. The only thing is you should be careful that before you push, before you do top plus plus and put the new value at topmost place, you should check for overflow. And overflow condition is very easy. If top has already attained the final element of the array, final position of the array, then announce it is overflown. Now, after learning first operation push, let's try to learn the second operation pop. Just imagine an algorithm for pop. What pop operation is going to do, it is going to take out the element. It is going to take out the element from the stack. So the summary of the pop is, if top is already minus 1, then we say there is nothing to take out from the stack. So we will print stack is underflown or stack is empty. But generally we say stack is underflown when there is nothing to be taken out of the stack. Otherwise, we will make some variable x. Let's take some x temporary variable and we will make equal to a top. That is, topmost element is loaded in a temporary variable x. After that, we will do top minus minus. That is, top becomes top minus 1. And finally, we will return the value of x. And here ends the else, and that ends the algorithm. That's the end of pop algorithm. Now, actually, this algorithm checks whether the stack is underflown inside pop itself. Ideally, when we write a program, we don't check for underflow inside the pop. We check the underflow in main. If main is calling pop, then main checks the underflow. But that's not our point of discussion. Let's very quickly find out how pop really works. It's very easy. Now imagine again that I am having a stack of 5 elements. So the element numbers are 0 to 4. That is, size is 5. Size of this stack is 5. And currently top is equal to 2. This is the array A, okay, array A. Now top is 2 means we have stored something in position 0 definitely, position 1 surely, and position 2. That's why top is 2, isn't it? Now let's call pop operation on this stack. What do you think? Which element should come out or which element should be deleted? It should be 30 because 30 is the last element that we have inserted or pushed. We push 10, then we push 20, and then we push 30. So 30 should be taken out first. That's last in, first out, isn't it? So let's start discussing the pop algorithm. First of all, we check for underflow. We ask, is top minus 1? Now, what is so special about it? Tell me, if top is minus 1, it means stack is empty, isn't it? Even 0th element is not filled if top is minus 1. Then we say there is nothing to take out from the stack, and we will print the stack is underflown. And we will not go to else and will not continue taking out an element. But right now you see that top is 2. Observe the value of top. Top is 2. So top isn't minus 1. The stack is not underflown. So we land in else. Now what will be x in this case? X will be top element of the array. Top element means second element of the array, which is 30. Isn't it? So x loads a value 30 and then top becomes top minus 1. So the new value of top, which was 2, will now become 1. Top is 1 now. What we have done is top, which was 2, has been taken down and top is now 1. So we say this element 20 is the topmost and 30 is as good as removed, isn't it? Yes, it should be, because now 20 is the topmost once the 30 is going to be taken out. And the last line here says return x, and remember 30 was that value of x. 30 will be returned back to the calling function. We have removed 30 and we have returned 30. I hope you are understanding. But one funny thing you observe about array is we are saying we have removed 30, but 30 will be still there. I hope you understand now. We have come long way. Notice that there is nothing called eraser here. There is no eraser which will remove 30 like this. Neither we can free the second element using some free function call. Free function can be used only in the case of malloc and dynamic allocation. So 30, we are claiming that 30 is removed, but 30 isn't removed. 30 is still there. What is important is the top counter, which was 2, now has been reduced and top is now 1. So it is as good as logically saying 30 is removed. Physically 30 is present, but logically 30 is removed because now the topmost element of the stack is 20, isn't it? Okay. Okay. Revise this with me. Call pop again. So what is pop going to do? First check for underflow. Stack is not underflown because top isn't -1. So let's land in else, and now this time x is going to be topmost element of the array. But topmost element of the array means first element, and first element of the array is 20. Then we will decrease top by 1. So top, which was 1, will now become 0. And it has to be, because if top was 1, now we have reduced this top and we have made it 0, isn't it? So we are claiming that 20 is as good as removed because 10 is the topmost now. Okay. And the final statement in the function, observe the last statement in the function after top equal to top -1 is return x, but x this time is 20. So we have taken out 20 and we are returning 20 back to the calling function. What will happen if you call pop again, third time? Obviously 10 will be removed, isn't it? I need not explain the entire pop now, but 10 will be removed. And what will top become? Top will become top -1. So top is now equal to -1. Top was 0. Now top becomes -1. This is good. If top becomes -1, it means that even 0th element is not present now and the stack is empty. Isn't it? The stack is empty. Now what if you call pop? If you call pop again, this if is going to be true, isn't it? If top is -1 is going to be true, and it's going to throw an underflow error. It won't go to else. It will throw an underflow error. Now, what's so funny about this algorithm pop is, just don't blame me, okay? But I am disclosing what blunder I have done. I am disclosing it in this video. Isn't it funny that this pop function, if it finds underflow, then doesn't return any value. But if it doesn't find an underflow, then it is returning an answer. This is bad. Because in our C function, we will write the pop function as follows, that pop function is returning an int. You can stop the video here in case this is not so important, but then I will encourage you to listen to what I am saying. In our C program, we will write int pop because pop is returning. Watch the last line. Pop is returning a value, isn't it? Now, what if there is an underflow? Check the if. If top is -1, we are printing underflow, and then we are not going to else. We are not going to else, and we are neither returning an answer, isn't it? Isn't it? Blunder. It's absolute blunder. We have promised that pop will return an int, and in the if part of the pop, we are not returning an int, and in the else part, we are returning an int. Just try this C function. Although I have not given such a C function to you, I have given an algorithm. Just try such a C function where function should return int, but if doesn't return an int, else returns an int. Forget it, compiler itself will give an error stating that function may not return a value, may not return a value. That's what I said. the underflow must be checked by the calling function. Calling function will check, can I call pop? If stack is underflown, better don't call pop. Okay, so if top is -1, calling function will not call pop itself. But if if the stack is not underflown, only then pop will be called. So basically, how is main going to call? How is main going to call the pop function? Just see this. I'll just make up some place. Now main is going to call the pop like this. If top is equal to -1, then print underflow, stack underflow. Else call pop. This will be written by the calling function. And once the pop is called, once this function is called, we are sure that it is not underflown. So no question of writing if, inside the pop. So there won't be any else either, and we will relax and we will just write these 2 lines, or rather 3 lines, that take out the value, store it in X, and reduce top by 1 and return X. But not to pressurize ourselves, we have seen a very simple methodology where we have checked the underflow inside the pop itself. We have printed underflow if top is -1, else we have done the pop operation. But I told you all this because maybe some person might see this video and make fun of your teacher or make fun of this algorithm. What kind of algorithm it is? We agree, but we can accept this as an algorithm, okay? But not in a C function. Thank you very much.